Hydrogen spectrum. When an electric discharge is passed through hydrogen gas at low pressure, a bluish light is emitted. When a ray of this light is passed through a prism, a discontinuous line spectrum of several isolated sharp lines is obtained. The wavelengths of various lines show that these lines lie in visible ultraviolet and infrared regions. All these lines observed in the hydrogen spectrum can be classified into 6 series. The first series is Lyman. This series lies in the UV region because it corresponds to electron transitions from higher energy level to the n equal to 1 energy level in a hydrogen atom. These transitions release photons with high energy and short wavelength. The second series is the Balmer series. This series lies in the visible light region of electromagnetic spectrum because it corresponds to electron transition from higher energy level n equal to 3, 4, 5, etc. to n equal to 2 energy level. The third series is Paschen series. All the wavelength of the Paschen series falls in the IR region of the electromagnetic spectrum. When electron transition takes place from higher energy state n equal to 4, 5, 6, 7, 8 to n equal to 3 energy state. The fourth series is bracket. Here the electron transition takes place from higher energy state n equal to 5, 6, 7, 8, 9 etc. to n equal to 4 energy state. All the wavelength of the bracket series falls in the IR region of the electromagnetic spectrum. Fifth series is the Font series. In this series, electron transition takes place from higher energy state n equal to 6, 7, 8, 9 etc. to n equal to 5 energy state. All the wavelength of the Font series falls in the IR of the electromagnetic spectrum. Sixth one is Humphrey. In this series, electron transition takes place from higher energy state n equal to 7, 8, 9 etc. to n equal to 6 energy state. All the wavelength of the Humphrey series fall in the far IR region of electromagnetic spectrum. How to calculate the wavelength of various lines of the spectrum of hydrogen and hydrogen-like species? By using the Balmer-Rydberg formula, we can calculate the wavelengths of a spectral line in any chemical elements. The formula was primarily presented as a generalization of the Balmer series for all atomic electron transitions of hydrogen. It was first empirically stated in 1888 by the Swedish physicist Johannes Rydberg, then theoretically by Niels Bohr in 1913, who used a primitive form of quantum mechanics. In this formula, where lambda is the wavelength of the emitted or observed light measured in meters, or h or r infinity is the Rydberg constant, which is equal to 1.097 into 10 to the power of 7 per meter. N1 and N2 are lower and higher energy orbit. Z is atomic number. It always 1 for hydrogen-like species. Let's solve this question. Question is, what is wavelength of light emitted when the electron in the hydrogen atom undergoes transition from an energy level n equal to 4 to an energy level n equal to 2. We have to find out lambda, the wavelength of light emitted. For wavelength, we use Rydberg formula 1 by lambda equal to or h z square 1 by n square minus 1 by n2 square. In this question, it is given that an electron jumps from an energy level of 4 to an energy level of 2, which means N1 equal to 2 and N2 equal to 4. If we substitute all the known values in this equation, we will get 1 by lambda equal to 1096 into 3 by 16. We know that there is a relation between wave number and wavelength. Wave number equal to 1 by lambda. So lambda equal to 1 divided by wave. Lambda equal to 60 divided by 10967 into 3. The value is 486 nanometer. Series limit of hydrogen spectrum. The last line of a spectrum is called series limit. Last line is the line of shortest wavelength. We take Balmer series for the studies. In 1885, when Johann Balmer observed a spectral series in the visible spectrum of hydrogen, he made the following observations. The longest wavelength is 656.3 nanometer. The second longest wavelength is 486.1 nanometer. And the third is 434.1 nanometer. Also, as the wavelength decreases, the lines appear closer together and weak in intensity. He found a simple formula for the observed wavelength, that is Rydberg equation. 1 by lambda equal to Rz square into 1 by n1 square minus 1 by n2 square. Here, for series limit n2 equal to infinity, you can get the limit of the series at the wavelength of 364.6 nanometer. Also, you can't see any lines beyond this, only a faint continuous spectrum. For series limit n2 equal to infinity, then the formula becomes lambda series limit equal to n1 square divided by Rz square. Find the value of short series of Lyman. For short series of Lyman, 1 by lambda L equal to R 1 by 1 square minus 1 by infinity square. For short series of Lyman, the transition takes place from infinity to n equal to 1 energy level. Here 1 by 1 square minus 1 by infinity square becomes 1 minus 0. So 1 by lambda equal to R. Lambda equal to 1 by R. The value is 913.4 Armstrong. Counting of number of lines in a transition. Here is a question. What is the formula for calculating the number of spectral lines in an hydrogen atom? Here is the formula. Calculating the number of spectral lines in an hydrogen atom equal to N2 minus N1 plus 1 into N2 minus N1 divided by 2. Next question is, how many spectral lines are seen for hydrogen atom when electron jump from N2 equal to 5 to N1 equal to 1 in visible region? In visible region, electron when jumps from N2 equal to 5 to N1 equal to 1, then according to the formula, possible lines equal to 5 minus 1 plus 1 into 5 minus 1 divided by 2 equal to 10. So the possibilities are 5 to 4, 5 to 3, 5 to 2, 5 to 1, 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1, 2 to 1. But here visible region is said, that is Balmer series. So x equal to 2 and y equal to 3, 4, 5. Thus the possibilities are 5 to 2, 4 to 2 and 3 to 2. That is, it shows 3 lines or lies in the visible region. Viewed Balmer lines. 4 Balmer lines were viewed by the naked eye. These lines are due to electron falling to shell 2. For numerical purpose, the Rydberg formula may be given as 1 by lambda equal to r z square into 1 by n1 square minus 1 by n1 plus x the whole square, where x equal to number of lines. X equal to 1, which means first line. X equal to 2, that is second line, and so on. n1 plus x equal to infinity for last line or last series. First line and last line. Last line is the series limit. First line is line of longest wavelength, line of lowest frequency, and line of lowest energy. Last line or series limit is line of shortest wavelength, line of highest frequency, line of highest energy.